Welcome to the complex numbers and quadratic equations. Today we will learn about the complex numbers and how to use them in the quadratic equations. This is the unit 4 of NCERT book. Okay, so this is good for class 11th to 12th students. And if 10th class students want to learn complex numbers in advance, this is the best video because it has all the basics of complex numbers. What we are going to cover in this is complex numbers definition, complex numbers system, transformation of power of I, algebra of complex numbers, that is addition, multiplication, subtraction, and division. Then modulus and conjugate of complex numbers. Then NCERT exercise 4.1 and NCERT exercise miscellaneous exercises. Okay. Also, I will add few of the BITSAT questions, important questions into this one, and I'll continue to make more videos about the critical questions of JEE and BITSAT, as well as I already started charts for complex numbers. Okay, you can continue to check that. Let's get into the complex numbers. Okay, so what is the definition of a complex number first? Okay, so we know that the equation x squared plus 1 equal to 0 has no real solution. That's because uh, when I try to solve this one, I'll get x square equal to minus 1 or x equal to square root of minus 1. And square root of minus 1 has no real number. All right. So to solve this problem, where ax square plus bx plus c equal to 0, okay, this is the quadratic equation, and determinant, let's say b square minus 4ac is less than 0. This has no real solution. Okay. Same as above. To solve these problems, okay, Euler has defined actually a new number system called complex numbers. Okay, because the solutions of these one does not belong to the real number system. So we have to extend the number system to include imaginary or complex part of it. Okay, so Euler defined I equal to square root of minus 1, I equal to square root of minus 1, or I square equal to minus 1. Okay, so to solve this, the negative square root problems. Okay, once you know that I square is minus 1 or I equal to square root of minus 1, you actually can solve several problems. Okay, so if a and b are real numbers and I is the imaginary unit, I equal to square root of minus 1, then a plus ib or a plus bi is called a complex number. Okay, and it is denoted by z, z equal to a plus ib or a plus bi. Okay, and the real part of z, re of c, it's written like that, is equal to a. Imaginary part of z, im of z, okay, so written like that, equal to b. Okay, and the two complex numbers z1 and z2 are equal if their real parts are equal and imaginary parts are equal. That is a plus ib equal to c plus id if a equal to c and b equal to d. So this is the basic definition of a complex number. Okay, now let's see how to solve problems using these complex numbers. Okay, so first is, okay, where is this complex number system? Number system is defined in the complete number system. Where is the complex number sits in? Okay, we know that complex numbers, which is in the form of a plus ib, which is above real number system, because real number system does not define any of square root of negative numbers. Correct. So we have to define a number system which is above real number system. So complex number system includes both real and imaginary. Okay, so the real number system is like a part of the complex numbers. Imaginary number system is IB part of the complex number. Okay, now imaginary number system just stops here. It is just IB. If you have square root of negative minus 1 basically, then it's called imaginary number system. That's it. Real number system, we know it has two parts. If you can write in P by Q form, okay, then we call it rational number. If you cannot write in P by Q form, then we call it irrational number. And the rational number has integers as well as integers. Okay, is a subpart basically. Okay, which is nothing but negative integers and positive integers. Okay, and negative non-negative integers, we can write it as whole numbers, that is 0 1 2 3 4 5. Okay, or natural number, which is 1 2 3 4 5 up to infinity. Okay, so this is where the system number system is defined, and complex number sits on the top. Okay, if you take only real number systems, then we have to take only this part. Okay, only this part. When you include complex number systems, you get the imaginary part of the number system. Okay, hope you understand where the complex number sits in the number system. Okay. Now, transformation of power of I. This is very important. Now, we said that I is equal to square root of minus 1 or I square equal to minus 1. Okay. Now, how the power, the I to the power of n plays a role. Okay. So, let's first write it continuously. I power 0 equal to 1, we know. Anything power 0 is 1. Okay. I power 1 or I is nothing but I, which is square root of minus 1. Okay, and I square is minus 1, I cube is I square into I square is minus 1, so it will be minus I power 4 is I square into I square, so minus 1 into minus 1, which is 1. Okay, and I power 5 is again I power 6 is minus 1, I power 7 is minus I, so it repeats. Okay, so the cycle is basically 4. After every power of 4, the cycle of I power n repeats. Okay, so there is a repetition of result of I power n. The result cycle repeats after 4 values of n. Okay, so which means you can do modulo 4 and then find out what is the value, right? So I power n equal to 1 or I or minus 1 or I depends on n modulo 4. Okay, 0, 1, 2, 3, right? 0, 1, 2, 3. Okay, if n modulo 4 is 0, you get 1, n modulo 4 is 1 you get I, 2 you get minus 1, 3 you get minus I. Okay. So, and also remember sum of consecutive I powers, sum of 4 consecutive I powers is 0, which means I power x, I power x plus 1, x plus 2, I power x plus 3 is 0. You take it, start from anywhere. Okay, minus I am starting with I cube plus I power 4 plus I power 5 plus I power 6. Okay, these consecutive values you have I, you have plus I, you have minus I, you have plus 1 and minus 1. So sum of it is 0. Okay, so any consecutive 4 powers of I, okay, is equal to 0. What kind of problems you can solve with this? Okay, most of the times you get I power some very big number. Okay, you just simply need to do like I power 67. You simply need to do I power 67 mod 4, which is nothing but I to the power of 3. I put I to the power of 3 is I square into I, which is minus I, right? This is the value. Any big I power, you can actually convert into one of the values, 1, minus 1, I or minus I. Okay, or it cannot be 0, right? Yes. Next, let's say sigma of, you get a problem something like this, sigma of k equal to 1 to 14 and I to the power of k plus I to the power of k plus 2. This is given. So you take the summation inside and it will become sigma of k equal to 1 to 14 I to the power of k plus sigma of k equal to 1 to the 14 I to the power of k plus 2. You expand this one. It will become I to the power of 1 plus I to the power of 2 up to I to the power of 14. And second one will become I to the power of 3 plus I to the power of 4 up to I to the power of 16. And we know that every 4 is 0. Every I power 1, I power 2, I power 3, I power 4 is 0. So what we are left with is up to 12 will go off I power 13 plus I to the power of 14. And in the second part, we are left with I to the power of 15 plus I to the power of 16. Right? And now if you see, these are also continuous. I to the power of 13, 14, 15, 16 are continuous. Again, this will become 0. So answer is 0. Okay. So such an expression, you can reduce it to a simple term. Either it can be 0, 1, minus 1 or anything. Right. So this is the use of understanding the power of I. Okay. Next. Okay. So algebra of complex numbers. Now let's understand how to add complex numbers, subtract, division, multiply, all those things. Okay. If Z1 equal to A plus IB, Z2 equal to C plus ID, be any two complex numbers. Okay. Then Z1 plus Z2 is defined as A plus C, the real part, summation of real part, plus I times summation of imaginary part, imaginary coefficient. Okay. B plus D. Okay. If you see, uh, B and D are having imaginary parts. Okay. I is there, right? So B plus D into I. Okay. So this is again a complex number, which means it follows the properties of any operation. Okay, following properties it will follow. This closure law, because sum of two complex numbers is a complex number again. Okay, we have seen here z1 plus z2 is a plus c plus I times b plus d. This is again a complex number, right? So summation is closure. Commutative law, for any two complex numbers z1 plus z2, z1 plus z2 is equal to z2 plus z1. So it follows commutative law. Also associative law, which is z1 plus z2 plus z3 in any order, basically. Okay. Then do we have additive identity? Yes, we have actually. What is that? It is 0. And 0 is nothing but 0 plus I times 0. Okay, then you add anything to it, you actually get the same value, right? So 0 is the additive identity, just like any sum operation. Okay, so z plus 0 is z, or 0 plus z is z. Okay, now do we have additive inverse? Uh, yeah, let's see. You have a complex number z which is equal to a plus ib. Okay, so additive inverse, if I add something to this complex number, I should get 0, right? Which is additive identity. So minus a minus ib is the additive inverse, okay, which is denoted as minus z. So z minus z is 0. Okay, z minus z is 0. So we have closure, commutative, associative, additive identity, and additive inverse. These are all possible in complex number addition. Okay. Similarly, let's see for the multiplication. Okay, multiplication is defined as z1 into z2 is equal to, you just multiply them, and then what you get is AC minus BD. Why minus BD? IB here, IB into ID is nothing but I square BD. I square is minus 1, so minus BD you will get. Okay, so it is a simple uh, a polynomial multiplication, x plus y into let's say a plus b. Okay, and then how you multiply, same way. Only thing is, take care, I square is minus 1, so I square term will become real part. Okay, so AC minus BD plus I times AD plus BC. Okay, this is how multiplication is defined. And multiplication also follows following properties. Closure law, definitely. Z1 into Z2 is equal to Z2. Z1 and Z2 is a complex number, right? So it's a closure. Commutative law is Z1 into Z2 equal to Z2 into Z1. You can just take any example and try it. Okay. Associative, definitely any order for the three complex numbers is possible. Multiplication. Okay. Multiplicative identity, does it exist? Let's check. If you take 1, okay, 1 is nothing but 1 plus 0i. 1 plus 0i. So 1 you multiply with any complex number, you will get back the same number. So we have a multiplicative identity. And multiplicative inverse. Okay. This is possible for every non-zero complex number. If a complex number exists, that means it is not equal to 0. Okay, which is a plus ib. Then we have a complex number which is a by a square plus b square plus I times minus b a square plus b square. If you multiply this number with a plus ib, you will get 1. Okay, z into 1 by z. We call it equal to 1. How do you get this a by a square plus b square? When you go to the modulus part, you will understand. This is nothing but square of modulus. A square plus b square is square of modulus. If you consider a plus ib as a simple two-dimensional coordinate plane, a comma b. So what is the modulus of a comma b, or this distance from the origin, is square root of a square plus b square. Okay, so this is square of distance, right? Square of distance of a comma b from origin, which is a square plus b square. And y minus, okay, this is the conjugate. When you learn the conjugate, you will understand this. Okay, so a plus ib multiplicative inverse is a minus ib divided by a square plus b square. Okay. Distributive law, yeah, this is applicable. Z1 into Z2 plus Z3 is equal to Z1 Z2 plus Z1 Z3. This is also possible. So multiplication has all these properties. Okay. Next, subtraction. It is very similar to the addition. Only thing is, it does not follow all the properties of addition. Whatever properties it is following, it may not follow here. Just like subtraction in normal number system, also same. Okay. So if Z1 is a plus ib, Z2 is c plus id, then subtraction is a minus c plus b minus di. Okay. Similarly, division. Yeah, division is possible. How to do is, first Z1 into 1 by Z2 you have to take. Okay. If Z1 by Z2 is nothing but Z1 into 1 by Z2. 1 by Z2 is inverse of multiplicative inverse of Z2. Okay. So which is nothing but, we have seen c plus id square root of c square plus d square. Okay. If you take this one, it's possible. Okay. Sorry, there should not be any square root. Okay. Basically, find out the multiplicative inverse of z2 and then multiply with that number. Okay. There should not be any square root here. Okay. You can find out when you find the multiplication inverse. At that time you get it. Okay. Next. One important thing is, I square is always equal to minus 1. In a complex number system, you have to assume I square as minus 1. Okay. And I is always equal to minus 1. See, I can actually write like this, right? I square equal to I into I, correct? And I is nothing but square root of minus 1 into square root of minus 1. And I take them into single square root. So square root of minus 1 into minus 1. So if I simplify the minus 1 into minus 1 first, it will actually becomes 1. Minus 1 into minus 1 is 1. So the whole thing will become square root of 1, which is equal to 1. Then I square equal to 1. But this is contradictory to what we defined I square as minus 1, right? So you can actually say that I square is also equal to 1. You can prove it very easy. But we have taken I square as minus 1 and then solving the problem. So you should never consider I square as 1 in a complex number system. Okay, this is very, very important note. Okay, this is where some calculation mistakes can happen. Okay, if you consider minus 1 and minus 1 inside square root and then cancel them, then calculation mistakes can happen. Okay, so I square is always minus 1. Okay, yeah, modulus of complex numbers. Let's understand the modulus part of it. Okay, if you consider z as x plus iv, iy, okay, why I took x and y, it very much resembles with the two-dimensional coordinate system x comma y, which is exactly same. Okay, where x and y are real and I equal to minus 1. So modulus of z is non-negative square root of x square plus y square is modulus of or absolute value of z. Okay, so you can represent like this: absolute value of z is square root of x square plus y square. Absolute value of z is always greater than or equal to 0. Don't take minus value of square root of x square plus y square. Okay, that's not correct. Okay, if you represent x plus iv as z, then two-dimensional plane. Okay, so z equal to x comma y. Modulus of z is length of x comma y from origin or hypotenuse of a triangle formed uh, with that on the axis, x-axis. Okay, so if you take z as 3 plus 6y, 6i, then we can actually represent it as 3 comma 6 in a two-dimensional coordinate plane. Okay, or in a complex number, we call it organ plane. Okay, something like this. Okay, if you take z as 3 plus 6 in a two-dimensional plane, it is pointed here because this is the origin. 3 comma 6, right? This is hypotenuse. 6 is the height, 3 is the width. Okay, x coordinate and y coordinate. Okay, this is how we represent. Okay, only thing is the plane is not called coordinate plane, it is called organ plane, which we'll just know. Okay, but it is exactly similar to what you have two-dimensional. So all those laws of two-dimensional plane will apply here also. Okay, conjugate of complex numbers. Okay, conjugate of a complex number z equal to x plus iy. If it is a complex number, the conjugate is defined as, okay, z bar equal to x minus iv. Okay, if you observe that only the sign is changed for the imaginary part, that's it. Okay, plus iv has become minus iv. Okay, if z is equal to a minus ib, then conjugate of z bar is z bar, conjugate of z or z bar, okay, is a plus ib. Okay, minus ib has become plus ib. This is the only difference. What is the use of this one? If you see, modulus of z equal to modulus of z bar, both are same. Okay, and multiplicative inverse of z bar or z inverse is equal to 1 by z, which is nothing but z bar by modulus of z square. Okay, so z into z bar equal to modulus of z square. Okay, once we know this, we know how to find out the inverse of a complex number. This is the usefulness. If you draw the graph of z and z bar, okay, it looks something like this. Okay, if you see the similarities, x comma y and x comma minus y are basically mirror image over x-axis. Okay, here in complex numbers, we don't call x-axis, we call it a real axis. Okay, x is real axis, y is imaginary or organ imaginary axis basically in a organ plane. Okay, so this is just a mirror image. They make exactly same angle alpha. Okay, only thing is sign will be different. Okay, this will be anti-clockwise direction, this clockwise direction. That's the difference. Okay. Okay. Properties of modulus and conjugate of complex numbers. There are several properties or formulae we can derive using z and z bar. Okay, I'm just listing all of them here. Modulus of z1, z2 equal to modulus of z1 and modulus of z2. Modulus of z1 by z2 equal to modulus of z1 by modulus of z2. where z2 is not equal to 0. Okay, z into z bar equal to modulus of z square. Z bar whole bar is equal to z. Okay, you conjugate a given complex number twice, you get back the same number. Modulus of z equal to modulus of z bar equal to modulus of minus z. All these are same. Okay, uh, z1 bar plus or minus z2 bar equal to z1 plus or minus z2 whole bar. Okay, so all these properties we can derive. These are all useful when you solve the problems. Okay, the plane having complex number assigned to uh, each of its point is called a complex plane or organ plane. Okay, this is what I was telling in the previous slide. Okay, we don't call it coordinate plane, we call it complex plane or organ plane. Okay, here we have two axes. One x-axis similar to x-axis, we call it real axis, and imaginary axis, which is similar to y-axis. It looks something like this. And if a plus ib, then a comma b is what we represent. So a comma b is represented in the organ plane in the same way as two-dimensional plane. So these are all the information, properties, and basics of the complex numbers. Now let's solve the problems. First, let's take NCERT simple problems, NCERT chapter problems. Then we add some more complex problems from the entrance exams and other. Okay, express in the form of a plus ib for questions 1 to 10. Okay, you have to express in the form of a plus ib. Okay, 5y times minus 3 by 5i. Okay, so this is very simple. Okay, you multiply the coefficients 5 into minus 3 by 5 and I square. I square is minus 1. So what you will get is 3 finally. So it is 3 plus 0 I. Okay. Another type is okay I9 plus I to the power of 9 plus I to the power of 19. So we know that I to the power of n repeats after 4 cycles, right? So which means we have to do n mod 4. So I9 will become I to the power of 1, same as I to the power of 1. I to the power of 19 is same as I to the power of 3. Okay, so I plus I to the power of 3 is nothing but minus I. So we'll get 0, 0 plus 0 I. Okay, I to the power of minus 39. So, okay, this is nothing but 1 by I to the power of 39, and then solve it similar way. And the important thing here is 1 by minus I. Okay, or 1 by I if you take. 1 by I is minus I. Okay, 1 by I is minus I. So how you will get? You multiply uh, numerator and denominator with I, then I by I into minus I. In this case, it is minus 1 by I. Okay, so it will become plus I. If it is 1 by I, it will become minus I. Okay, so this is the important one. Note down. Yeah, other things I think are straightforward. You can do it yourself up to 10. There is uh, nothing special in this. Problems like 1 minus I whole power 4, you uh, apply the polynomial equation, power equation correctly. 1 minus 4 plus 6 and minus 4 and plus, and properly write it. Wherever I square is there, it is minus 1. I cube is minus I. Okay, and if you get I power 4, it is 1. So all that you properly write, then you will get the answer correctly. All are same actually. Okay, next. Find the multiplicative inverse of 11 to 13. Okay, so first one is 4 minus 3i. This is let it be a z. Then 1 by z equal to z bar by modulus of z square, right? So z bar is nothing but 4 minus 3i is the given complex number. So z bar is 4 plus 3i divided by z square, which is nothing but 4 square plus 3 square. So multiplicative inverse is 4 by 25 plus 3 by 25i. Okay. All are similar. So just do it. Okay. Next. Express the following in the form of a plus ib again. So here you have complex products are given. So first thing is numerator and denominator, solve them independently. Okay, and then whatever you are left with. Okay, suppose in this case if you solve numerator and denominator, what I'm getting is 14 divided by 2 root 2 I, which is nothing but 7 by root 2 I, but I is in the denominator, so it will become minus I, right? So minus 7 by 2 root I, which is nothing but 0 minus 7 root 2 by root 2, 7 root 2 by 2 I. Okay, you can write whatever way you want. Yeah, let's do the miscellaneous exercise part also in the NCERT book. Okay. I to the power of 18 plus 1 by I to the power of 25 whole cube. Okay. So, yeah, this is again simplification only. I to the power of 18, you can write it as I square plus 1 by I to the power of 25, you can write it as 1 by I to the power of 1. Okay. So, I square is minus 1, 1 by I is minus I. So, if you replace it, what I will get is minus 1 minus I whole cube. Now, you apply A plus B whole cube formula here, and you will get 2 minus 2I. For any complex numbers z1 and z2, prove that real part of z1 into z2 equal to real part of z1 into real part of z2 minus imaginary part of z1 and imaginary part of z2. This is very simple. You take two values, z1 equal to a plus ib, z2 equal to c plus id. Okay, once you take this one, it is a straightforward question. z1, z2 equal to, you will get ac minus bd plus ad plus bc I. Okay, which is nothing but real part and imaginary part, right? Real part of z1, z2 equal to AC minus BD. Real part of z1 into z2 also minus imaginary part of z1 and z2. Okay. Okay. Reduce this into the standard form. So whenever you find I in the denominator, first thing is you do multiply with the bar. Okay. Conjugate. All right. Then you will get the answer directly. Everything you will get in the numerator. Right. So in this case, we can actually take LCM also. Okay. So try with the LCM. Okay, if you take LCM, this is LCM and this is, so numerator and denominator you simplify, and then finally bring it into uh, numerator and denominator, bring it into A plus IB form, and then you apply conjugate of it. Okay, so 28 minus 10i was there in the denominator, so I'm multiplying numerator and denominator with 28 plus 10i. Then this is the answer you'll get. Okay, x minus iy equal to square root of a minus ib divided by c minus id. Prove that x square plus y square whole square equal to a square plus b square divided by c square plus d square. This is a straightforward question. Okay, so x minus I equal to given value. Then I want to remove the I from the denominator. So what I will do, I will multiply numerator and denominator with c plus id. Okay, then this is the value I'll get. AC plus BD plus AD minus BCI. Okay, divided by c square plus d square. Now, I minus x minus I whole square equal to, if I square it, this is what I will get. Okay, remove the square root basically on the RHS side, which is equal to x square minus y square minus 2xy. Okay, so comparing the real and imaginary part, x square minus y square is the real part, which is equal to AC plus BD divided by c square plus d square, and minus 2xy is the imaginary part, which is equal to AD minus BC divided by c square plus d square. Now, x square plus y square whole square is equal to x square minus y square whole square plus 2xy whole square. So, just to substitute the values correctly, simplify it, you will get a square plus b square divided by c square plus d square. That's what we want to prove. Okay, z1 is given as 2 minus I, z2 is 1 plus I. Find the modulus of z1 plus z2 plus 1 divided by z1 minus z2 plus 1. This is a straightforward question. Substitute the values first. Okay, and check the denominator and remove the denominator. Okay, by applying the conjugate of the denominator, multiplying with this. Okay, so you will get in terms of I. Okay, no denominator. So which is modulus of 1 plus I, which is nothing but square root of 2. Okay, a plus ib equal to x plus y whole square divided by 2x square plus 1. Prove that a square plus b square is the expression given here. Okay, so this is also a straightforward question. We have done before similar one. Okay, first simplify it. First simplify it, and then a is equal to real part, b is equal to imaginary part. Okay, and a square plus b square equal to its value. Okay, and then simplify that. Okay, you will get x plus 1 whole square equal to x plus 1 whole square divided by 2x square plus 1 whole square. Just a simplification. Okay, it's just like a polynomial. There is nothing much about complex numbers here except taking the real part and imaginary part correctly. Next, z1 equal to 2 minus I, z2 equal to 2 plus I. Find the real part of z1, z2 divided by z1 and imaginary part of 1 by z1, z2. Okay. So z1, z2, if you multiply, this is what you will get, minus 3 plus 4i. z1, z2 divided by z1 equal to, simplify, what you will get is 2 by 5 minus I. Okay, so real part is 2 by 5 is the first question. And 1 by z1, z2 is 1 by minus 3 plus 4i. If I simplify, I'll get minus 3 by 25 minus 4i by 25. Okay, so this is minus. Okay, this is minus. So imaginary part of 1 by z1, z2 is minus 4 by 25. Next, find the real numbers x and y if x minus iv plus 3 plus 5i is conjugate of minus 6 minus 24i. Okay, yeah, simple. This is multiply the x minus iv and 3 plus 5i, write it properly in real and imaginary part, and then we equate it to conjugate of minus 6 minus 24i. Okay, so if you compare, you will get two equations: 3x plus 5y equal to minus 6, 5x minus 3y equal to 24. You solve these two equations, you will get the answers: x equal to 3, y is equal to minus 5. Okay, find the modulus of 1 plus I divided by 1 minus I minus 1 minus I divided by 1 plus I. Okay, yeah, simple. Take the LCM and then simplify it, numerator and denominator. What you will get is 2i simplification. So modulus of that is 2. Next, x plus iy whole cube equal to u plus iv. Show that u by x plus v by y equal to 4 times x square minus y square. This is a simple proof. First thing is, yeah, expand x plus iy whole cube. Then compare with the imaginary part and real part. Okay, so u is equal to x cube minus 3x y square. U divided by x equal to x square minus 3y square. Similarly, v is equal to 3x square y minus y cube, and v by y equal to 3x square minus y square. You sum these two, u by x plus u by y, what you will get is, and simplify, 4 times x square minus y square. Just straightforward polynomial question. If alpha, beta are different complex numbers with modulus of beta equal to 1, then find beta modulus of beta minus alpha divided by 1 minus alpha bar beta. Okay. So yeah, these are two different complex numbers. So first thing is, you take beta minus alpha divided by 1 minus alpha bar beta modulus and then square it. Okay. Why we are squaring? Just to remove the modulus part. Okay. So which is equal to, we know, modulus of complex number square is equal to z times z bar, right? Z is modulus of z square equal to z times z bar. So that's what I took it here. Beta minus alpha divided by 1 minus alpha bar beta multiplied by this bar of this one, z bar. Okay, and you take the bar inside, it will go into every term. Okay, bar will go to every term. So beta bar minus alpha bar divided by 1 minus alpha bar is alpha and beta bar. You simplify it carefully, this is what you will get. Okay, so given that z and beta bar equal to 1, so substitute beta modulus of beta equal to 1. Okay, modulus of beta and modulus of beta bar both are equal to 1. Okay, so this expression will become alpha into alpha bar is modulus of alpha square. Then beta and beta bar is modulus of beta square, which is 1, because modulus of beta itself is 1, modulus of beta square also 1. Okay, and this value you simplify it further, which is equal to 1. Okay, so if you see, numerator and denominator is same, which is 1. So the given expression here is equal to 1. Next, find the number of non-zero integral solutions of the equation modulus of 1 minus I whole to the power of x equal to 2 power x. Okay, yeah, this is simple. Modulus, right? Modulus of 1 by I is equal to square root of 1 plus minus 1 whole square, then power of x, so which is equal to nothing but root 2x, which is equal to 2x. Okay, So this is possible only if x equal to 0, right? Square root of x is equal to 2 power x is possible only if x is equal to 0. So x is equal to 0 is the solution, only solution. But he is asking non-zero integral solutions, which means there are no possible solutions. Number of possible solutions are 0. Okay, given complex number, product of four complex numbers is equal to a plus ib, then show that this given expression. Okay, modulus of product of modulus of each one equal to modulus of the combined one. Okay, so this is also you just apply modulus independently. Okay, and modulus of 4 z1 and z2 is equal to modulus of z1 into modulus of z2. So if you apply that principle, it will become modulus of each individual one. Okay, then square on both sides, you will get a square plus b square times c square plus d square times e square plus f square plus g square plus h square equal to a square plus b square. This is a straightforward proof. Okay, very simple. If 1 plus I divided by 1 minus I whole power m equal to 1, find the least positive integral value of m. Okay, first thing is simplify 1 plus I by 1 minus I. You multiply the denominator with its conjugate, both numerator and denominator, and simplify. What you will get is I to the power of m. Okay, so I to the power of m equal to 1, which means m values start from I to the power of m is equal to 1 means m should be 4 minimum, right? So m starts from 4, 8, 12 and so on. Okay, which means the least positive integral value of m is 4. Yeah. So these are the NCERT questions. Now let's do the critical questions. Very few I collected, but I will do more videos based on competitive exams. Right now, I just covered the BITSAT questions in this. Let's do them. Let Z1 and Z2 be nth roots of unity, which subtend a right angle at the origin. Then n must be in the form of what? Okay, n must be in the form of what? Nth root of unity, right? So this is what he's trying to tell. Okay, if you have two uh, Z1 and Z2, 2 points, and if you draw a line from 0, they subtend a right angle at the origin. Means Z1 angle Z1 O Z2 equal to 90 degrees. Okay, it's not 90 degrees showing 90 degrees here, but what I'm trying to tell is alpha minus theta equal to 90 degrees basically. That's what I'm trying to tell you in the image. Okay, so given that angle between Z1 and Z2 is pi by 2, arg of Z1 minus arg of Z2 equal to pi by 2. Okay, arg is nothing but angle it makes with x-axis, that is real axis. Okay, in this case, arg of Z1 is alpha, arg of Z2 equal to theta. So alpha minus theta equal to pi by 2, which is given. So which is nothing but arg of Z1 by Z2. Arg of Z1 minus arg of Z2 equal to arg of Z1 by Z2, which is equal to pi by 2. Okay. So Z1 by Z2 equal to, okay, if Z1 by Z2 is a complex number, okay, it makes an angle of 90 degrees with the x-axis, which means the complex number will be cos pi by 2 plus I sin pi by 2. Okay, this is the one which makes 90 degrees with the x-axis, right? Which means it is nothing but I, because cos pi by 2 is 0, sin pi by 2 is 1. So Z1 by Z2 equal to I. Okay, now given that Z1 and Z2 are nth root of unity, Z1 by Z2 to the power of n equal to, which is nothing but Z1 by Z2 is given as I, so I to the power of n, that means equal to nth root of 1 whole to the power of n, which is equal to 1. I to the power of n equal to 1. This is what he's trying to tell. I to the power of n equal to 1. This is what we derived right. Okay. Once you know this, he is asking what is the question? N must be in the form of, what is the form of n? N has to be in the form of 4k. Okay. How? We know that I to the power of k equal to I to the power of k plus 4, I to the power of k plus 8 and so on. Correct? So, and I to the power of k equal to 1. When it will be 1? When it is minimum power of k is 4. 4, 8, 12 and so on, which is in the form of 4k. Right? This is in the form of 4k. Okay, so n is in the form of 4k. That's the answer. Hope you understand this. Next. Okay. If modulus of W equal to 2, then set of points Z equal to W minus 1 by W is contained in or equal to the options given. Okay. So this is the interesting question actually. At first sight, you will actually see two answers correct, but only one of them is actually correct. Okay. So let's see. Modulus of W equal to 2, which is given, which means W is nothing but 2 times cos theta plus I sin theta. I can write it like this. This is what I'm assuming W. Okay. Because its modulus is 2 and cos theta plus I sin theta, we know modulus is 1. Okay. 1 by W will become 1 by 2 times cos theta plus I sin theta. If I simplify it, I'll get 1 by 2 cos theta minus I sin theta. Okay. Cos theta minus I sin theta. Now, Z equal to W minus 1 by W, which means if I take W value here, 1 by W value here and simplify it, I get 3 by 2 cos theta plus I times 5 by 2 sin theta. Now, what is the real value of Z? 3 by 2 cos theta. Modulus of it is 3 by 2 cos theta, which is less than or equal to 3 by 2. Correct? Because cos theta maximum value is 1. Okay. So, from this one, actually, from this one, answer C looks correct. From this value, real value of Z is less than or equal to 2. Right? Answer C looks correct. But it does not define Z completely. Does it tell anything about the imaginary part? So this answer looks correct, but it is not defined Z completely. Okay. So let's continue it and find out what about the imaginary part. Modulus of Z equal to square root of 3 by 2 cos theta whole square plus 5 by 2 sin theta whole square, which is equal to this value. And if I simplify further, I'll get 5 by 2. Okay. This is, sorry, I'll get square root of 4 sin square theta plus 9 by 4. Okay. And we know that sin square theta maximum value is 1. So if I substitute 1 here, I'll get 5 by 2. Okay. Now 5 by 2 is nothing but less than 3. Okay. Now this means modulus of Z is less than or equal to 3. This is also correct. There are two answers looks correct. Out of the two, we have to choose D as the right choice because C does not define Z completely. Okay. He is asking set of points Z is contained in or equal to. Okay. You need to define Z correctly. Okay. Z is not defined correctly with answer C. So D is the right answer. Okay. So this is very tricky question. In BITSAT 22, it is asked. Next. The smallest positive integral value of n such that given expression is purely imaginary. Okay. So if you are telling something is purely imaginary, that means its real part is 0. So first is simplify the expression, simplify the complex number and then equate it. Okay. So we know two things, 1 plus cos theta equal to 2 cos square theta by 2. Okay. Uh, and sin theta equal to 2 sin theta by 2 cos theta by 2. Okay. We need to apply this because how do I remove this plus 1? I need to remove plus 1 from this. Okay. Um, so this is one way. Okay. So what I will do is first is sin pi by 6. I will write as cos pi by 2 minus pi by 8. So sin pi by 8 is equal to cos pi by 2 minus pi by 8, which is cos 3 pi by 2. And cos pi by 8 equal to sin 3 pi by 8. You shall replace them. Okay. And then 1 plus cos theta. 1 plus cos theta is nothing but 2 cos square theta. So I am replacing with 2 cos square 3 pi by 16. And then sin theta equal to 2 sin theta by 2 cos theta by 2. With this, what is happening is I can take cos theta common and cancel. I am getting in this form. Okay. Very simple form. If I call 3 pi by 16 as theta, then it is nothing but cos theta plus I sin theta divided by cos theta minus I sin theta whole power n. Okay. And we know that ei theta, okay, this is one thing we should know. Very important to note down. E to the power of I theta equal to cos theta plus I sin theta. Okay. This is Euler's formula. You can easily derive from logarithms actually. Uh, so note down this one. And e to the power of minus I theta equal to cos theta minus I sin theta, conjugate basically. Okay. So given expression will become this expression. This expression will become e to the power of 13 by 16 pi, correct? Sorry, I 3 pi by 16 divided by e to the power of minus I 3 pi by 16 whole to the power of n, right? This is cos theta plus I sin theta, cos theta minus I sin theta. So I will write in this form. Now this is e to the power of minus, so it will go to the numerator as positive, so it will become e to the power of uh, 3 pi by 8 and whole power n I am bringing in, so it will become e to the power of I 3n pi by 8. Okay, so I can write this back in this form, cos of 3n pi by 8 plus I sin 3n pi by 8. This is the final expressions. I simplified version of this one. Okay. Now, once you know this, it is given that this is purely imaginary. That means the real part is 0. So, real part is nothing but cos to the power cos 3n pi divided by 8 equal to 0. This is possible only if 3n pi by 8 equal to pi by 2, 3 pi by 2, 5 pi by 2, and so on. Right. So, solving the integral value of n, what I will get is n is equal to 4, 12, 16, and so far. Okay. Right? So smallest positive integer is what is asked actually. Smallest positive integer which is equal to of n which is equal to 4. 4 is the smallest value. Okay. Hope you understand this. This is very important equation actually. E to the power of I theta equal to cos theta plus I sin theta. Note down this. Next. The root of equation 2 times 1 plus I square x square minus 4 times 2 minus I x minus 5 minus 3 I equal to 0, where I is square root of minus 1, which has greater modulus. So which means the question asked is basically they have given a quadratic equation in complex coefficients. Okay, and then asking us it has two roots and which modulus is greater. Okay, so very simple. We have to just to solve it like a quadratic equation. Okay, so this is the given expression. Solve it just like a quadratic equation. Okay, so A is equal to 2 times I plus 1 plus I, B is equal to minus 4 times 2 minus I, C is equal to minus 5 minus 3I. So B square minus 4AC is simplify, you will get 64. Okay, now X is equal to minus B plus or minus square root of B square minus 4AC by 2A, which means it is nothing but 4 times 2 minus I plus or minus 8 divided by 2 times 1 plus I. Simplify it, you get two values. This is my first value, 16 minus 4I divided by 4 times 1 plus I, or minus 4I divided by 4 times 1 plus I. Take the first one modulus, simplify it, you will get square root of 34 by 2. Take the second root modulus of it, okay, which is root 2 by 2. So which one is the greater modulus? Obviously, this 34 by 2 is the greater modulus. So this is my root actually. This is my bigger root. 16 minus 4I divided by 4 times 1 plus I. If I simplify it, I'll get 3 minus 5I by 2. I should always write in the complex number format. That is A plus IB format I have to write. I cannot have complex number in the denominator. So I should simplify that. The answer is 3 minus 5I divided by 2. This is the answer. Yeah, thank you. So this is all about the complex numbers. Very simple concept, but it can solve many problems, real world problems in the physics as well as in mathematics. Okay, so keep learning, uh, practice more complex number problems. I will come up with more and more videos and start watching my shorts also on the complex numbers. Thank you.